So in the previous lesson I forgot to mention that I basically added a Vellum input-output. It's this node, Vellum IO. I set it to explicit. I set my path, the frame range, apply the color to the geometry output, and merged in the ground. So now we have this, and you can see what the result of the simulation. It looks pretty good for me. There's a little bug here, the tail that's wiggling a little, which is weird, but we're gonna fix it in the next iteration. But the compression of the muscles looks nice. The bubbles are not overly inflating, so I like it. We have this result because before I spent a lot of time tweaking the parameters and trying to dial in the values that work well, so this is why in the first long iteration we have this result, but usually it takes quite a lot of iterations just to test the simulation. So and the parameters, we have the sliding of the tail here as we planned. Then yeah, we have a bunch of stuff happening here. So yeah, the next step would be applying this animation to our quad mesh to see how it looks, and use that quad mesh as a source for the flip simulation. This is not the whole simulation, it's just 115 frames, so it's enough for a preview. Sometimes I split the model into pieces, just for example I isolate one tentacle just to see if it works. So I'll give you an example. So basically if you have this as a model, sometimes I would come here, put a blast node in the middle, and yeah, I would select really a piece of my geometry. So instead of selecting this, yeah, so click again and select some points. I would do this, delete non-selected, and I would simulate only this piece of geometry. So yeah, this would allow me to have faster iterations, but it depends on the dynamics. Here we will see just that the arm is going to be just throwing itself, and then this part of the body is going to follow. Because we don't have any tail constraining the body to the ground, it's going to be a little bit chaotic. So it works in some scenarios, it depends. But yeah, I advise you to, when you try simulations like this, I advise you to go into your microsolvers, disable a bunch of them, and then simulate again. So I prefer to just simulate separately each microsolver, with each microsolver like separate the simulation into several steps, see if separate things work properly. Yeah, so I'll disable this. Just to recap what we did here, we had a tetrahedral, we had a quad mesh, we grouped a bunch of stuff together, we painted some masks, we separated bubbles, we had a remeshed object, then we animated it with the help of some attribute triangles. We transferred the animated attributes to our tetrahedral mesh. We had a to our triangulated. Oh yeah, we copied some attributes, animated attributes to our triangular mesh, and then time shifted our triangular mesh. We tetrahedralized it, transformed it into volumetric tetrahedrons. We transferred some groups. We created an IDS attribute. We also set some custom properties. The vector called their arm, which defines the direction of the contraction of our muscles. We applied some density, stretch stiffness, using our relative B-box expression in the Z direction, which allows us to have some really great control over our density. So if we stretch stiffness, and then we have density. So these are parameters that define how heavy the mesh and the object is in separate parts of the body. Then we transferred the live attributes onto our tetrahedral mesh. We attribute blurred, so it blends better into between the vertices. Then we had a master transform that defines the initial placement of our monster above the ground. So you see it's barely above the ground for the initial drop. Then we set some Vellum cloth constraints, which define the bendiness and the stiffness of the surface triangles. The surface triangles, if you remember, were created by the tetconform with this checkbox. So it's a separate additional layer on top of the tetrahedral mesh, which allow you to make some kind of wrinkles there. But if your mesh is not dense enough, you'll barely see those wrinkles. I added it just so I could show you the default, like the initial, the meta setup for these kind of simulation. Then we created the Vellum tets. We applied some tetrahedral stretch constraints with a model called nonlinear ARAP, which is as rigid as possible, which tries to maintain the volume of the tetrahedrons as much as possible during deformation, and we applied those constraints to our group, which is called GRP TETs, tetrahedrons only, not the surface. The density was multiplied by a attribute, which we created earlier, the density. Then we had the thickness calculated uniformly over all the vertices. And then, same with the stretch stiffness. We multiplied it by the stretch stiffness attribute. Then for the fibers, we applied the TET fiber constraints only on the group called GRP legs, which is a point attribute, point group, and the stiffness was set to 0 because it's going to be controlled inside the Vellum solver. So inside the Vellum solver, we created a subsolver, inside of which we're importing our rest geometry, which is this geometry, the outrest, which is the geometry that has the live attributes cycling through. So in the subsolver, we're basically transferring the live attributes onto the DOP network geometry. Then we're sampling data from the ground. So before, initially, as far as you remember, we tried this locomotion test here in the subs just to see if the forces are transferred. We created a FRC debug force here, which is the resulting force without any multiplication. We visualized it to see if it works properly as we intended it to work. And then once we were done with the sub test, we transferred the same VOP inside the subsolver right here, locomotion test. So it does exactly the same but over time. So this is the magic node, which just samples the velocity and the normal from the surface. The velocity is just a directional -1 vector in the z-axis. We normalized the forces, we added them together, multiplied them by CDR. The CDR controls the normal force, if it's negative or positive over time. So the CD is the attribute that activates the force only on the tips. And so the CDR is really crucial here. And then we safely added the force to the existing force. So the force here, we take the force here, and then we add our resulting force to the existing force, and we apply it to the force, not the velocity. This is crucial because this is the safe method of adding. We can do it in the velocity, but there's a lot of other stuff to consider. I'm not going to cover this here, but for now it's just know that you have to, in this case, you have to add it to the force. So so this is the subsolver. The subsolver pulls the live attributes, and so they exist in this simulation, updated live on each frame. Then we created this geometry wrangle that reads the constraint geometry. So it reads the constraint geometry, checks if the constraint is of a specific type, which is ARAP, the as rigid as possible constraint. If it's not, it doesn't do anything. If it is, it just takes our dir arm attribute and rotates it with a quaternion attribute, which is a default attribute contained in any tetrahedral mesh with the TET stretch constraints applied to it. The rest vector is the initial alignment orientation of the tetrahedron. So with the help of this rest vector, which is updated live during simulation, we rotate our V dir arm so it points always into the direction of the deformation of our legs or arms or tentacles, however you may name those. Then we have this, oh well, that would have been a mistake. If I scroll like this, it's going to increase the number, so let's be careful there. We created the Vellum constraints microsolver, which is creating constraints between the tips and the ground at a specific time, and then another Vellum constraint properties, which takes those constraints, processes them, only them, and checks if the color of the vertices attached to those constraints is bigger than 0. If it is, it's going to kill them off with the use of this dummy remove property. And then we have the animate contract, which takes the fiber constraints we created earlier in the sub context, and it takes the color of those vertices related to the fiber constraints and applies the stiffness to them. So if it's white, it contracts. If it's black, it just releases. It doesn't expand, it just releases. So it doesn't, it removes the contraction basically. So the muscle becomes relaxed. Then we created another Vellum constraints attached to geometry. After the frame 5, between the group tail ends, which is the tail of our creature, and the ground force, we set also the crucial thing here is the sliding rate, which allows those constraints to slide along the surface. they're attached, but they have some freedom. If the sliding rate was 0, they would have the possibility to move. So the arms will pull, but the whole body would stay in place because these constraints do not allow the creature to move. And finally, the bubbles animate, which is also a Vellum constraint property. Microsolver, which takes all of the stretch constraints, which is the whole body, and then it checks if those constraints are related to vertices in the group called group bubbles. If they are, then there's a fitting happening, which is taking the color of those bubbles and fitting them in between 1 and the max inflate value, which is 3. So between 1 and 3. So when the bubbles are black, the inflation is 1, which is basically the default state, the uninflated bubbles, the rest bubbles, and then max inflate is 3. So the rest length of these triangles and the tetrahedrons inside is going to multiply by 3. Relatively speaking, because there's connectivity involved, so sometimes they do not inflate to 3 because there's limits where those constraints try to stay as rigid as possible, so they do not allow inflation above some values. If we were to use another type of constraint, like for example, if we go to this, to linear ARAP and uncheck preserve volume, they would be able to expand almost limitlessly, but the stability of the simulation would be completely different, and there might be things that would explode. So here we go. We have this setup. I'm pretty happy with the result. This setup is quite clean compared to the initial. The setup I had before was just a horror because it was kind of a playground for me. I was playing around with nodes, but this is a really condensed and compressed and a really short version of the tutorial. I mean, not short version of the tutorial, but it's the essence of the locomotion system I developed. So yeah, let's see what we do next. I will just apply, in this tutorial, I'll just apply the motion to our quad mesh, and then we'll see what we can do next. So let's pull our quad mesh. I'm going back here to the top, creating an object merge, putting this into the object. This is how I like to do the merging. And so into this object, and now we have this quad mesh, but as you can see, it's penetrating the ground, and this is because we have a master transform to respect. So you have to respect this master transform. So we'll just have to apply the same master transform to the quad mesh before we do any transformation or motion transfer. So we right click on the master transform, and in the action you do a create reference copy. So this is a trick where you can transfer the same positioning rotation as our tetrahedral mesh. And now we're going to drop a point deform. In the first input goes our clean mesh, and we're going to drop a time shift. The time shift delete channels, so it goes in the second input, and the animated version of the tetrahedral mesh goes into the point deform. So yeah. And as you can see, we have our quad mesh moving, and it's cool. One thing to mention is that the output mesh, as you can see, it's tetrahedrons. So what I'm going to do here, just clean the mesh. The only thing I'll be leaving here is remove this or this, remove all the attributes except V and CD. So I'll uncheck the color because it was for preview purposes, not for the final result. And or we may just like this. We have our mesh here, and then let's see what I'm going to do here. I'm going to just bake this mesh so we could have faster feedback. And we have tetrahedrons here. So one thing to mention is you see that we have polygons, we have tetrahedrons. What I prefer to do is always do the point deform from the tetrahedrons. Basically the motion, I love when there's tetrahedrons transferring motion to a poly mesh, because the tetrahedral mesh contains volume and volumetric tetrahedrons, and they deform, and if they help a lot with the motion transfer through the point deform sometimes, because the point deform is basically a prim-UV wrangle that just takes primitive attributes and transfer them to the points. And if you worked with XYZ distance and prim-UV, you know what I'm talking about. And if you didn't, it's alright. It's just a a method of sampling data from primitives, which is very precise, and it works really well with motion. So I'll be changing these parameters. I really want the mesh to be precise, so I'm going to change the radius to 0.005 and the minimum points to 10. It's for more precision. So if you template this, yeah, there's a lot of precision there. 5, yeah, something like between 5 and let's say 50, 25, nothing changes. If you do it like this, the averaging of the motion is going to be less precise. So I'm going to use a smaller radius and a minimum of 5 points. This is enough for the motion transfer. And another thing I want to do is transfer attributes. So I want to transfer the color, because we have the color and the V. There's a bunch of attributes that Vellum outputs, but I want to transfer only the velocity and the color. So points to points, color, velocity. So here you go. I'm gonna sample this. So as you can see, there's color. What we're going to do with the color is apply the color only. This color will be used in the shader. So this is, let's increase the sample count here, and the distance threshold, I'm gonna lower it down. So yeah, and as you can see, we have the velocity transferring to the quad mesh, because initially the point deform doesn't do that. It doesn't transfer any attributes, so you have to do it by yourself. So the color attribute is going to be used in shading for changing or blending in between two shaders. And yeah, so the normals, and what we're going to do else, it's attribute cast, like an attribute that I love a lot. It's just great. What it does is it just takes any attributes and removes some digits from the data. So if you look closely in the spreadsheet here, let's see what it does. We have normals, velocity, and yeah. So you see the velocity has 6 digits after the dot here, and the attribute cast. And we'll type in V and CD here, because this is what I want to trim some data, and I'm going to set it to 16-bit float. You'll see the difference instantly. So if you mouse wheel click on the attribute transfer, you see that the memory is 2427, and after the attribute cast it's 2268. This is what happened. It just trimmed a few megabytes, which is great, but with huge geometry and particles you can see a big difference in data amount. It gets trimmed. Nothing visually changes, because if you disable or enable it, you don't see any difference. But if you look here, we have 6 digits after the dot, after the separator. But if you do the spreadsheet on the attribute cast now, yeah, basically it lowered the precision. And if we go here, let me find some intermediary. Yeah, so it trims some values here, adds some other values there. But yeah, it saves data on trimming values that are not really, like, it lowers precision basically. So yeah, we're gonna save this as a with a file cache. So I'm going to do it as explicit. I don't want to deal with the versioning now, because I have too many versions in my life. Sim main clean quads v01 f5 bgusc. So yeah, I'm going to load it from disk, and we're going to simulate again. I'll see what I can do about the wiggling tail and come back to you about it, and say explain to you why it does it. Resimulate and save this file cache. So now you have a recap of what happened there. I'm gonna make this box smaller. This is the Vellum setup, split by groups. Yeah, we are a little bit over the just organizing. So I'm gonna separate this like this, pull it back, make a box for cleanup. This is gonna be the cleanup. And that's okay. And now we're gonna isolate the Vellum here. The Vellum is going to be in this area. Let's color it green. Vellum setup. Now this is going to be the cleanup 2. Cleanup 2 and motion transfer. Alright, so we have some network boxes here. And this one is going to be grouping. Yeah, so is going to be import and groups, just so we keep everything organized, especially for people that are coming after you. So yeah, something pale, kind of like this. So now you have network boxes everywhere. And this one's going to be on the side here. Sometimes it's really hard to follow through the tutorial. I know how it is. Sometimes I find tutorials that are not really explaining anything, just clicking left and right, but there's no explanation why it's done and how data circulates. Especially in Houdini, you need that kind of explanation. There's a lot of stuff to consider, and there's a lot of stuff happening under the hood. And once you get used to the data flow and how attributes circulate through those pipes, you'll start understanding stuff and debugging faster any problems that arise during simulation. Method 2. Alright, so this is alright. We can save this. It's time to save. It's funny that I didn't save at least one time during this. This was really dangerous. So yeah, we have to go and activate the autosave just so. So in the edit you click autosave and you'll have it autosave as many times as you set in the parameters and the options. So yeah, next step, once I save all of these files, the clean quad geometry and the resimulate this one. I mean resimulate first and then save the clean geometry. Once I do that, we're gonna switch to doing the FEM simulation with the wrinkles, and after this it's going to be the flip, and after this we're gonna switch to shading our scene and rendering this bad boy. See you in the next one.